Going to record here. Come on, there it is. Start. And I'm going to go ahead and start sharing. As usual, if it looks like that I'm just babbling along and not sharing, please interrupt me and say, Mr. Pierce, do you mind sharing? And yes, yeah, okay, so here I am. Everybody see the little girl? Okay, good. That's my check to make sure that life is grand. All right, so what do we have here? We have a periodic table. Now, last Friday we were doing these box configurations. Remember that? Okay, and so we're going to do something called an abbreviated electronic configuration, or just an electronic configuration is generally what we call it. Okay, and so what we're going to do is, first off, I'm going to change colors here so it'll draw on the black, is I'm going to put helium right here. Okay, now helium is a noble gas. It is true. It is a noble gas and it belongs over here. But the thing about helium is that it doesn't have a p shell. You remember when I said you have S shells, P shells, D shells, F shells, and all that? Helium doesn't have a p shell, whereas neon, argon, krypton, xenon, and radon do have a completed shell, but they also have a completed p shell. Okay, so to make it work for the electronic configuration, which I'm fixing to show you, I need to put the helium over into right next to the hydrogen. Okay, it's just to make things work. And if you look at some periodic tables, you will actually see that helium actually shows up in two different places. It sure does. It depends on the periodic table, believe it or not. There's not just one periodic table. There's actually more than one version. Okay, having done that, I moved it over into helium. And what we're going to do is I'm going to try to sketch this carefully, okay? As carefully as I can, because I'm not an artist, believe it or not. And what we're going to do is we're going to go from here to here. We're going to call this the S block. And I did this last time too, but we're going to do it a little bit more carefully now, okay? And we're going to call this whole section between, in this valley, I call this a valley because to me on this periodic table, this is a valley through here. See, it's kind of like a valley. That's why I call it a valley. All right. And so we look through here, and we're going to call this whole section through here the D block. And that's going to run all the way from here to there, okay? And that's going to be the D block. And we're going to put everything else over here, we're going to put in the P block, all right? And by the way, it's lowercase p. It's hard to tell with a P. But you know what? If you use an uppercase S or an uppercase D or an uppercase P, it's okay. It's okay. It's just a matter of style. Many things, believe it or not, as we get deeper into chemistry, many things will come down to style and preference. It doesn't mean you can do anything you want. Just understand that depending on which part of the world you're in at the time, they may say or do things slightly differently. All right, just keep that in mind. So uppercase, lowercase, I go in between. You know, sometimes I do uppercase, sometimes I do lowercase. All right, so we have S, D's, and P's, and this block right down here, we call these the F elements. Okay, those are your F elements. Those are just two lines there. Now, this is where I really wish that I was in the classroom, because in the classroom we have a ginormous periodic table that I can point to. Now, it's kind of hard for me to point on the screen, but do y'all, just out of curiosity, I'm wiggling around underneath the D. Do you see my little cursor? Do you see a little cursor underneath the D? No, you see what I mean? I mean, I see a cursor, y'all don't. This is where it would be nice if I was standing in front of the class. Okay, it's one of the limitations of what we're doing. All right, so I have this laid out into an S, D, and P and Fs. Now we're not going to do anything with the Fs as far as electronic configurations. However, I will point out that these guys, and I think this might have been a quiz or a homework question, these guys are called the rare earths. That's what they're called, okay? And rare earths are used in a lot of things before we get into electronic configurations. They're used in a lot of things, particularly cell phones and electronics and strong magnets, that sort of thing. And they're called rare earths, but believe it or not, they're not particularly rare, even though they're rare earths. All right. They're of great strategic importance. China has a lot of the rare earths. They process most of them. All right. And then we have these guys down here. We call those the lanthanides. Okay. And really the only important things on the lanthanides are these two guys right here. And let me clean this up just a little bit. And americium, which is AM, that's in smoke detectors. Okay, americium is the smoke detectors. Uranium, plutonium are the pixie dust that makes nuclear power plants and nuclear weapons work. All right. None of the other stuff is really of much interest, except maybe to researchers on out of the lanthanide. Uranium is used in power plants and in nuclear weapons. Plutonium is almost exclusively used in nuclear weapons, and that's to blow up entire cities. All right, so I mentioned that because you need to know, and that these are F elements. Now, if you look over here, let me draw your attention right over. Let me change color just a little bit momentarily here. Look over here. You see where I'm drawing in blue? Do you see how it changes numbers? It jumps. It goes from 57 to 72. And that's because the way the periodic table is arranged, the F elements actually come out of the board. They actually come out. They come out into the lanthanides. And if you look at element number 57, which is La, well, sure enough, that's lanthium, and the lanthiums have similar chemical properties. They're like their own group. They are the F elements. They literally come out of the board. Same thing with the actinides, number 89. See how it goes from 89 to 90? It jumps over to 103 and it comes back to 104 with ruthenium or hafnium with 72. You know, it comes out, comes in. And so rather than print out periodic tables with this 14 element section sticking out of the board, we just snip it off at the board and lay it down. That's what we do. We snip it off and lay it down because it literally comes out of the board, back into the board, and back across. Okay, so there's your lanthanides with your F elements. Okay, but we're not going to worry about the lanthanides unless you go into mineralogy or geology and you actually are going to run around out in the wilderness with big dump trucks. Some of you may decide you want to do that. Then you will care about these things. But for us, we don't care. So since I don't care, I'm now going to erase all this. All right, so now I have mentioned it. I have done my duty. And there they are, okay? I have done my duty. And never to be mentioned again will be the F elements, okay? But they're there. They are there. All right, so we're going to focus on the S, P's, and D's. Okay, so we have the S elements, which is 2 elements wide, and we have the D elements, which is 10 elements wide, and we have the P elements, which is 6 elements wide. And you can count for yourself and see that it's 2 wide for the S's, 10 wide for the D's, and 6 wide for the P's. Now, if you recall, how many electrons can an S level hold? It can hold 2. How many electrons can a p sublevel hold? It can hold 6. And how many can a d hold? 10. These are our sublevels. And how many orbitals can each one have? Well, your s level has 1 orbital because it has 2 electrons maximum. Your p sublevel has 3 orbitals because it has 6 altogether. Remember, it's 2 electrons per orbital, and the d has 5 orbitals because it has 10 electrons maximum. Okay? And I think someone emailed me over the weekend and said, Mr. Pierce, that one question just wasn't fair. And it said, well, how many orbitals are in, let's say, the n equals 2? Or something like that. And you know, the n equals 2 would, and we're going to go over this, would include the 1s orbitals, the 2s orbitals, and the 2p orbitals. That would include all of those orbitals. Okay, so when you talk about an n level, you include everything. Your s's and p's are sublevels. Sub means part of. Okay, so don't confuse, you know, our subshells with the entire shell. The entire shell, every time, now this is important, I'm going to draw this down here now that we're moving on here. Every time you finish a row, every time you finish here on up, this is a completed shell. Okay? Every time you finish a row, it's a completed shell. There's a reason why the noble gases are not particularly reactive. It's because they already have completed shells, and everything is trying to have a completed shell by either gaining, losing, or sharing electrons. Okay, so every time you hit the end of the row, it's a completed shell. This is important. Now, going over here on the other side, I'm going to number these rows, these periods. This is 1, 2, 3, 4, 5, 6. Okay, I'm just going to number down through 6. There's more. Okay, there's more. Let's see. Meeting info, lock meeting. Okay, so I have numbered the periods. Okay, now the rule that we're going to use is going to look like this. Now, an electronic configuration looks like this. Let me just write out a random, and I'm going to use this periodic table for everything. Let's just write out a random period, my pen's messing up on me. Here we go. This is just a random electronic configuration. Okay. Now remember, when, last Friday we did box configurations. All right, and this is similar to the box configuration, but you don't have the boxes. And what do we have here that's important? First off, this number right here in the front, this number right there, is the primary, or the N number. All right, that's the primary, the N number, that first number. And it is the same as the row period for your S's and P's. Okay, it's the same as the row number for the S's and the P's. For your D's though, n-1 equals your D's. Okay, n-1 equals D's. So your row number, as long as your S's and P's is the same as the quantum number, the primary quantum number. When you drop into the D's, it's 1 less. So if you look at your D's, look at SC, element number 21. When you hit element number 21, it's not going to be 4D, it's going to be 3D, because what's 4 minus 1? 4 minus 1 is 3. Okay, so your D's is the row number minus 1, or n minus 1. Okay, all right. And so now we're going to use this information to figure out, to get this electronic configuration. Now, the S's and P's that are up here, let me change colors again. And so you see that there are S's and P's, and those are the subshell, or your, remember that, or your L. L being 0 to n minus 1, right? 0 to n minus 1 are the allowed values of the subshell L. Now, this is what causes a lot of people confusion, is right here. You see that 6 and you see that 1. Those don't mean anything mathematically. They just mean number of electrons in subshell. That's all they mean. Number of electrons in the subshell. If you look at it, it almost looks as if, actually, there's no almost about it. It really looks like it says S to the first power, or S to the second power, or even better yet, 2p6, it says P to the 6th power. It looks like that. It really does. But it's not. It's not. It literally is how many electrons. You got 1 electron, 2 electrons, 3 electrons, 4 electrons, 5, 6. You have 6 electrons. That's all it means. It's not a mathematical. I used to think that before I was corrected. I was allowed to think that. I'm not going to allow you to think that. Okay. The S sublevel is a mathematical description, and it does tell you something about the shape and all that. And the P does tell you that it's, shaped like a pair of dumbbells or whatever. Okay, this is true. And the 2 and the 3 does mean that it's a particular primary quantum number. Okay, but the exponent, it's not an exponent, it's just a count. Okay, it's just a count. And I want you to be very careful here too, as we do this. That number that's above the P, or above the S, is how many you have in that particular subshell. It is not the total number of electrons. Total number of electrons is like the 17 in chlorine. That's total number of electrons. Now, do you remember Friday we also did valence electrons? Where's the valence electrons? Valence are your outermost electrons, right? And so this would have 1, 2, and we're going to ignore the middle. This would be 3, 4, whoops. That would be 4. This would be 5, 6, 7, 8. I'm trying to be very neat about this, okay? And so those in blue at the top are your valence electrons, which are what? The outermost electrons. And so when we do these electronic configurations, and we're about to do this after I finish showing you all this, we will see, based on the electronic configuration, where the valence electrons are. They're on the outside. Just like people, the only thing we're interested in is on the outside. Same thing with the atoms. It's the outside that's all exciting. Okay, and so there you go. All right, so let's go ahead and do some electronic configurations. Let me show you how to do it. All right, let me erase some of this. I'm gonna go all the way out here and erase. Like I said, I'm gonna try to use this particular periodic table, okay, just so it's consistent. All right, so let's take a look at hydrogen. Let's take a look at hydrogen. And the way we're going to do this is we're going to write a bracket H for the element that we're trying to find the electronic configuration of, okay? There it is. And here's the rule. Here's the order. We always start with hydrogen, always. And number 2, we go left to right, and number 3, we're going to top to bottom. Start with hydrogen. We're going to start with hydrogen. Start with hydrogen. We're going to go left to right, top to bottom. This is how we're going to do this. And we're going to use our periodic table to help us, because the periodic table is laid out according to the electronic structure of atoms. And so that's why we can use the periodic table, because that's the way it's laid out. And okay, so hydrogen is on row 1. So it is N1. It is in the S block. The hydrogen is in the S block. So we say it is 1S. It is, now, how many electrons are in the S block for hydrogen? Just 1. And so we say 1S1. 1S1. Okay? And that's how we say it, by the way. We say 1S1. We don't say 1S to the first. We say 1S1. Literally, 1S1. Okay, well that's hydrogen. That's not terribly exciting. Let's do helium. He, same deal. Now what I said. We start with hydrogen and we work our way left to right, top to bottom. So we are on row 1. And so row 1 is n equals 1. Remember, that number in the front means n. Same as the row number for S's and P's. It's 1n. So it's 1. And so where do we start with hydrogen? Hydrogen starts with the S block. So it's S. And we count across 2. We go 1, 2. Remember, I put helium up there next to hydrogen temporarily. That's because I want the helium to be an S block. And so helium has 2 electrons in the S block, so we say it's 1s2. Notice how I said that. I didn't say 1s squared. I'm telling you this because I used to do that. And I don't want you to do that. I don't want people to look at you strange, okay? I want you to be able to say, yeah, that's yeah, helium, that's 1s2. And it is 1s2, okay? So we are finished with row 1. So let's drop down to row 2. And we say row 2 starts with lithium. There it is. There's lithium. And we say it equals. We're looking for the, now, what's the rules here? The rule here is we start with hydrogen every time. We work left to right, top to bottom. Well, hydrogen is row 1. Hydrogen goes from hydrogen to helium, and that's your S elements. And there's 2 electrons in that first block starting with hydrogen. So this is row 1. Row 1 is 1s2. It's hydrogen 1s1, helium 1s2, and we stop at 1s2. Now we can drop down to the second row, and we say, well, the second row where lithium is row number 2, and it is, where is lithium? It's in your S block. We haven't left the S block because that's all you have in the row 1. And row 2, we start with lithium. We say, well, that's in our S block. And so we say 1s2, 2s. All right, now, how many electrons do we have in that 2s block so far? Just 1. And so we say 2s1. All right, now look, remember what I said? I said that top number is the number of electrons in the subshell or sub-level. I use 2 terms interchangeably. They really mean the same thing, sub-level, subshell. What is 2 plus 1? You look up there. What's 2 plus 1? It's 3, right? What is element number 3? It's lithium. many electrons does lithium have? The lithium has 3 electrons, 2 of which are going to be in the 1s2 level, and 1 of which is going to be in the 2s1. They add up to 3. Do you see that? Okay, they do add up. That's why I'm saying, don't get these numbers confused with the grand total. The maximum you will ever have in an S level is 2. The maximum you ever have in a P level is 6. The maximum you'll have in a P subshell is 10. The grand total can be, 117 or whatever. All right. So let's do the next one. Let's do beryllium. And so we have beryllium. Now remember what I said. We start with row 1 with helium, and we say helium 1s, hydrogen 1s2. We're finished with the first row. We drop down to the second row and we say 2, well, that's the second row. And we say we're in the S element so far, and that's 1s. And we go lithium is 2s1, and we say beryllium is 2s2. We're literally counting. We're using our periodic table to count. So we go lithium 1, beryllium 2, 2s2. But look, you still have to have that previous row. We always start with hydrogen. All right, let's drop off to another one. All right, I'm just working left to right. Let's do beryllium. I'm sorry, we just did beryllium. Let's do boron. Let's do boron. We start with hydrogen. We say 1s, 1s2, that's our first row. We drop down to the second row and we say, you know what? There's lithium, 2s, 2s2 with beryllium. And then we jump across. Look what I'm doing here. I'm jumping across. You see that? I'm jumping across to the from the beryllium to the boron. Where is the boron? It's in row 2. Boron is in row 2. But what kind of element is boron? Boron is a P element. It's the first one in the P elements, but it is on what row? It is on row 2. It's still row 2, even though I jumped across. See how I jumped across with that blue arrow? But now we're in the P elements. And how many electrons do you have in that 2p subshell? Just 1. Just 1. Remember what I said. Do not confuse the total electrons with what's in the subshell. Okay, it's the first boron has the first electron in the 2p subshell. And so therefore it's 2p1. Now, remember what I also said. The superscript is the number of electrons. So we count this up. We go 2, 4, 5. 2, 4, 5. What element is boron? It's element number 5. You see that? It has to add up. All right, it has to add up. All right. Now, let me go ahead and fix this up just a little bit here. There we go. Now let's jump across to fluorine. Let's just jump across to fluorine. Okay, let's make it a little bit more exciting, if that's possible. And we go fluorine. All right. So why don't we try this? Okay, I've shown you how to do the S's and P's. Why don't you type fluorine's electronic configuration in the chat box, and you don't have to do the superscript. Just try to separate, go 1s, do it separated by space, like 2s, 1s2, 2s2. You see what I'm saying? Just separate them out by space. And go ahead and type that in the chat box. Let's see if we can get the same answer for fluorine. We get the same answer for fluorine. Let me make that F look just a little bit nicer. There it is. All right, let's see if we can get this. Put it in the chat box. You should be able to just bang this out pretty quick. As long as you have a periodic table in front of you, you ought to be able to do this, okay? What do you get? Let's put it in the chat box. Let's see if we get fluorine together. Maria says 1s2, 2s2, 2p5. And Riley says the same thing, 1s2, 2s2, 2p5. Know how I'm saying, see how I'm saying that? 1s2, 2s2, 2p5. It's not 2p to the fifth, is what I'm getting at, okay? All right, so you know what? Looks like everybody's got that one. So let's say 1s2, start with the first row, drop down to the second row, and then count across 1, 2, 3, 4, 5 to fluorine, and there it is. Okay, there it is. All right, let's do one more. Let's do a third row element. So I'm going to erase all this. I'm going to erase all this now. I hope you're getting the joke. You know, like I said, there's a you may have learned it a different way. It's called the Aufbauer principle, the Aufbauer, and it's a vastly more complicated way of doing it. I don't show that because as long as you have a periodic table in front of you, you can do this. So let's have everybody do sulfur. All right, let's go ahead and do sulfur and put that in the chat box. Let's put that in the chat box. What is sulfur? What is sulfur? You tell me. And once we do that, and once I'm satisfied everybody at least has an opportunity to do a third row element, we'll do D elements next, and then exceptions, and then we'll be done with chapter 6. JD says 3p4. That's good. Got another one said 3p4, and Emma says 3p4. And literally, if you can count row 1, row 2, 1, 3, and you can move left to right and don't, skip over anything and just go all the way from left-hand side to the right-hand side, you can do this. You can do this. And so what's S? S is 1s2. That's the first row. We go to the second row. We start with 2s2. We jump across to where neon is, and we go 2p6. That would take us to neon. And then we're heading to sulfur, so we jump down to the third row and we go 3s2. And then we count across the sulfur and we go 1, 2, 3, 4, and we say 3p4. That's what we're looking for, sulfur, right? Everybody get that? Did you get that? Did I mess this up? Did I get it right? Let's see. 3s2, 3p4? I think I got it right. Did I get it right? Y'all look confused. Yes or no? Is that good? Okay, good. I want to make sure, because remember, I don't have you in front of the class, and if you start looking confused, I get worried. All right, I don't want you to be confused. The whole point of this is not to confuse you. All right, so we have that. Now, when we're looking at valence electrons, though, how many valence electrons does sulfur have? And we look up here at the blue numbers, and we see that sulfur has what? 6 valence electrons, right? For sulfur. Where are the valence electrons? Well, the valence electrons are on the outermost. Where are the outermost? It's your 3s. Your highest ends. What's your highest end here? 3. So you got, look here, 2 and 4 gives me what? Your 6 valence electrons. Y'all see that? Yeah, there they are. There are your valence electrons. They're right there in front of you, okay? Now, it is common to, especially when you start getting into the higher elements like this, is to take all these guys right here from the previous shell, and we call those core electrons. We call them core electrons. Those are the ones beneath the valence electrons. We call them core electrons, and oftentimes we will abbreviate this whole mess here because it can get pretty big in a hurry, and all we care about what's on the outside anyway, right? And so what is the 2p6? Well, 2p6 is neon. That's 2p6. You see that? So we can actually write sulfur like this. We can say sulfur, and we can say, you know what? It has a neon core, which we don't care about. And then we have the 3s2 3p4. It's a bit less writing. It's a bit less writing like that, okay? And this is called the noble gas configuration. Why is it called the noble gas configuration? Well, look, what's neon? Neon's a noble gas. It's the core electrons is in neon, okay? It's the previous shell. It's the previous shell, okay? So when we looked at sulfur, the previous shell is what? Neon. Okay, previous completed shell. So we pick up where we left off. Now this is important here. Oftentimes, if you're gonna mess up doing a core electrons or noble gas configuration, you have to start where you left off. Neon left off on the row number 2, right? So you got to pick up with row 3. Common mistake would be to say either 2s2, 2p4, or to say 1s2, 1p4, or something crazy like I can barely say it. You know what I'm saying? It's so wrong. But make sure you pick up where you left off. All right? All right. S's and P's. There you go. S's and P's. We should be able to do the S's and P elements all day long. All right, let's do it D elements. We're almost done here. All right, now D elements, on the other hand, are these guys, which I have marked with D, right above the blue wavy line. Those are your D elements. Let's take a look at iron. So we have iron. Now, if we were to write out iron, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6, we would write out all that. But let's just use, and I'm gonna erase this up here. Let's use our noble gas configuration for iron. Where's iron? Iron is right here in blue. There's iron. That's where our goal is, right? What's our previous shell? Argon. And so we would say argon. Now remember, we have to pick up where we left off. Where are we leaving off? Right here with the 4. See it on the periodic table? See the 4? And so we're going to say 4s. And how many do we have here? We have 2. We go potassium is 4s1, calcium's 4s2. Remember, we're going left to right. Now, what do we know about the D elements? The D elements start with n minus 1. What's row minus 1? What's the row? It's row 4. What's 4 minus 1? It's 3. So our D elements actually start with 3. And so we say 3 for our first row here. For our first row, this is the 3s. These start with 3. Okay? They start with 3. And so we say 3D and we go 1, 2, 3, 4, 5, 6. 3D. It helps if I put the D in there. 3D6. Wait a minute. 1, 2, 3, 4. Wait a minute. Is that 5? 1, 2, 3, 4, 5, 6. It is 6, isn't it? Isn't it 6? Am I counting right? 1, 2, 3, 4, 5, 6. My eyes get crossed first thing in the morning. It is 3D6. All right, so we have 4s2, 3d6. Fantastic. And so something like zinc, element number 30, would be what? It would be 4s2, 3d10. Y'all see that? Easy peasy. You just got to count. The only big thing about the D elements is you have to, the D's start with 3. All right. So what if we were to do, say, bromine? Let me change colors here if I'm going to go over there. What would we do with bromine? Well, bromine would be the same sort of situation. Bromine is still 4th row, right? What's previous filled shell from bromine? Argon, right? And so we would literally say for bromine, we'd say argon. We'd still have 4s2 because look, you have to finish up where you left off, and you're working left and right. You're starting with the S elements on the left-hand side, 4th row with potassium. That's 4. S's and P's are same as the row. But the D's start with 3, so we'd say 3D. We look all the way across the zinc. Zinc is what? 10. And we pick up where we left off. We're still on row 4. With element number 34, gallium, we're still on row 4. And so what's the S's and P's? Same as the row number. We say 4. And bromine would be what? 1, 2, 3, 4, 5. It would be 4. Let me make that a lowercase p. 4p5. Because this is still row 4. Still row 4. Just because you went through the D's doesn't change the fact that the S's and P's start with the row number. So it goes 4s2, 3d10, back to the 4s, 4p5 for bromine. Okay? So keep that in mind, and don't try to put them in order. Don't go like 3D, then the 4s, 4p. That's the order that they fill in. Okay, and the reason why they change orders is because, remember what I showed you about the splitting and all that, and I said some of the levels split, all right? Well, that's because some of the levels split lower than the others, and some split higher than the others. Okay, so they end up with lower level. Not terribly important, but just know that's the order that they fill in. All right, questions on this so far? This is one of these things where there's like a little switch.
Why is bromine 4p5 and not 4p7?
Oh, that's a great question. Why not 4p7 for bromine, right? Okay, well that's a legitimate question. Well, let's take a look up here for bromine. Let's take a look. Remember what I said, these are p elements. All these guys are p elements where bromine is, right? And P's is max 6 to begin with. Okay, because the S's is max 2. All right, now let's just hold that thought for a second here. And so when you count across into the P elements, you start counting over again with the P's. So we would literally go, well, where's my bromine? There it is. We would literally, let me change colors here to red. Here's bromine, right? And so we would say 1, 2, 3, 4, 5, and that would be 4p5. Okay, because we're counting cross. 7 would include these guys over here if you included the 7, but the 2 electrons over here are already 4s2, the 2 electrons. So it goes 4s1 for potassium, 4s2 for the calcium, and then we start all over again for the P's, and we go 1, 2, 3, 4, 5 for the P's. So it becomes 4p5. There are 7 valence electrons, though.
Gotcha.
Yeah, you got it now. And so the 7 valence electrons would be 4s2, 4p5, 7 altogether. You see that? Do you see it now?
I think so.
Okay. There it is. So 1, 2, 3, 4, 5. And we do the same thing up here. 1, 2, 3, 4, 5. And that same thing up here. 1, 2, 3, 4, 5. Same thing down here. 1, 2, 3, 4, 5. Okay. So if we were to take oxygen and on down, oxygen on down, what would be the configuration? It would look like this. It would be N, the row number, S to the 2, and then it would be N, the row number, P to the 4 for all the oxygen on down. Here's oxygen on down. They would all follow this format right there. You see that?
Yeah.
So no matter which row you're on, the oxygens are going to be below oxygen is going to be P4. No matter where you're at with the halogens, which bromine is 1, what are the halogens? The halogens are NS2NP5. Bromine being NP5, which would be what? 4P5, right? 4S2, 4P5. Chlorine would be 3S2, 3P5. Fluorine would be 2P5, 2P2, 2P5. See what I'm saying?
I think so.
Yeah, all the way up, all the way down. It's the same one. All right. Now, that was a great question, let me tell you, because if you look at that, you would think, well, why isn't it 7? Well, it's because you don't want to double count. If you count 7 there, you would be counting the S elements twice in a sense. Okay. All right. Other questions. Other questions. What do we got going on Wednesday? Don't we have a test? Yeah, I think so. I think there is a test Wednesday. We're going to finish chapter 7 today. That's for sure. All right. Now I'm almost done here. Let's look at our 2 important exceptions. Let me erase what I have up here so far. Let me erase all this. All right, let's take a look at these exceptions. You remember what the exceptions were when we were looking at the boxes? The exceptions were what? They were chromium. They were chromium and copper, weren't they? And so here, let me erase these guys. Continue erasing, okay? Give me a second here. Alrighty, so I kind of erased my board a little bit. Give me a second here. So what were our 2 exceptions? Our 2 important exceptions were chromium and copper. Now, when I said important exceptions, it was according to the electronic configuration. And so if we were to write out chromium starting out, doing it just the way I showed you, we would say, and we're going to do noble gas configuration. We'll start with argon. We would predict that we would have, well, so we're starting on the 4th row, so it'd be 4s2. The D's start with 3. See how I'm talking myself through this. I say, they start with 4, 4s2, the D's, and we would go 1, 2, 3, 4 to the chromium, and we would say 3d4. This would be our predicted. We would predict this would be the case. But what did we see in that box configuration that we did last Friday? We saw that the S would promote over to the D, and the actual would end up being, the 4S would end up being promoted, one of them. So now we have 4S1, and now we have 3D5, which is half filled D. Okay, just like the box configuration. So this would be the actual. If you go out and do an experiment, you would see that the D shell on the chromium is actually half filled. It's not 3D4, it's actually 3D5, which is halfway. All right. And if we do the same thing for copper, we would predict that we'd finish up with the previous shell, which is argon. We would pick up with the 4S when we'd say 3D, and we count across to the copper, and we'd say 3D9, and that's what we would predict. But in actuality, what ends up happening? The 1 electron gets promoted into the D from the S, And so we end up with actual is copper Cu. And it's now, once again, it's 4s1 because where'd that one electron when it went to the D, except this time it filled up the Ds to make 3d10. And now we have a filled D, and that's actual for the copper. Okay, so these are your two important predictions that violate what you'd expect from what you'd see up there. All right, you'd expect the copper to be 3d9. In reality, it's 3d10. And you'd expect the chromium to be 3d4, but in reality, it's 3d5. Okay, they're important. These are two important exceptions. Now, having said that, y'all may have noticed I said, not quite the case, kind of like that, because, I want you to know reality. Okay, I don't want you to know pure theory, because the world is not nearly as neat as some people would have it believed to be. Well, it's true that you would predict all the way down, you would expect these guys to be behaving just like copper. After all, they are in a copper group, they are in a chromium group. This is true. But you start getting down in here and you actually start seeing, the 1s's, the one electron off the s's get promoted. So it's not just the chromium group on down and the copper group on down that this sort of thing happens to, where you get the s's get moved around. It actually happens on other elements as well, besides those. But we focus on the fourth period, or the 3Ds, because it's a pretty neat little thing. It's like, oh, look here, nature likes to be half filled or full filled. And it's true, it does, but it also deviates in other ways as well. So don't get hung up on that it has to be that way. It doesn't. Okay, once you get down into that fifth and sixth row, all bets start getting lost. All right, so that is it for chapter 6. Any questions on this before we move on to chapter 7? All right, so chapter 7, I promise you, will not take that long to do. All right, chapter 7 is not going to take that long. It's going to take, it's hand waving is what it is. In other words, I just wave my hands around and say, this is the way it is. And you go back to the textbook and you look at the details. Okay, that's what we're going to do. Is we're going to look at it from a very general sort of way with chapter 7, and that's what you need to know. So I'm going to show you what you need to do. It's going to take me about 45 minutes to go through it. Okay, about 45 minutes to go through chapter 7. It's the shortest chapter in the entire book. I swear it is. All right. So what we'll do is, since it's almost 11 o'clock, we will take a break, as we so often do. I have promised you that we will take breaks. And we're going to take a break, and we're going to go to, let's say, I like 11:07. I don't know why, but I do. All right, so we're going to take a break to 11:07 a.m. I'm going to go ahead and stop recording, and I'm going to stop recording right up here as well. And hopefully